Let's welcome the speaker.
Thank you. It's a long day, isn't it? So I'll try to make it simple and quick. I thought about presenting some really hot recent results, but the last minute decision was to minimize such thing for because it's not that much interesting yet. So I'm trying to concentrate on some recent histories of this line of research of designing non-binary or including binary sequence families using Sidelnikov sequence, which is very interesting subject in this area. And this work is done jointly with Professor Kim at Yonsei University. So in the beginning there is a Sidelnikov sequence. In a Russian paper, 1969, he introduced two different types of non-binary could be possibly binary sequences with low non-trivial autocorrelation value, meaning the out-of-phase autocorrelation is very low, so it's quite favorable for an application to various communications engineering and a lot of other designs. And those two sequences are now called as power residue sequences, which is of period P for prime P, and another is now called Sidelnikov sequences of period Q-1. So these two sequences are quite different, but has very similar properties. In 1977, these three authors have rediscovered these Sidelnikov sequences only for binary cases. It says a class of binary sequences. And for a while, it is called Sidelnikov-Lempel-Kohn-Eastman sequences for a while, but now it was happening. It happens even for IEEE transactional information theory that the same thing is rediscovered many times. Anyway, so power residue sequence is defined by following. Given prime and a divisor of P-1 and primitive root mod P, we partition the set of integers mod P into coset of subset of mth powers, and then define a sequence to be either 0 when t is 0, because that doesn't belong to any of the coset, and to be number k when the index t belongs to the coset c sub k. It's very simple, and Sidelnikov sequence is a bit more tweaked. So we now consider all possible finite fields of size q, and M is a divisor of Q-1, and similarly we partition the non-zero elements of field into coset of mth powers, and then the Sidelnikov sequence is defined to be either 0 or k when beta to the t plus 1 is 0, and if beta to the t plus 1 belongs to the kth coset of the mth powers. I'll try to explain by example here. P is equal to Q is equal to 13, and the 3 divides 12, and we took 2 as a primitive root mod 13, and cubic residues mod 13 are 1, 5, 8, 12, and its two cosets are called C1 and C2, multiplying the first power of 2, the second power of 2, respectively. So 1, 5, 8, 12 term of the sequence contains are 0, and the 2, 10, 3, 11th term are 1, and 4, 7, 6, 9th term are 2. So that's very simple. For Sidelnikov sequence, we have to calculate the successive powers of primitive root and one more than that, and then reverse back to the index so that 2, 7, and 11 becomes 5, 12, and 8 belongs to C0, so it's going to be value 0 like this. 2, 7, 11, 2, 7, 11 has value 0, and 3, 4, 5, 9, which corresponds to 9, 4, 7, 11, 9, 4, 7, 6. That's C sub 2, so has value 2. These are different, and one has length 13, the other has length 12. Okay, so in one page, they look very much the same except the condition that T belongs to C sub K or beta to the T plus 1 belongs to C sub K. So originally the Sidelnikov's introduction contains only the property of low autocorrelation of these sequences. So in the middle of 2004 or 5, I thought about why not, or can we construct a family using these non-binary sequences so that the cross correlation is also comparable, or we say good cross correlation, in terms of either lots of, say, Welch bound or lot of bounds are known to say whether cross correlation value is good or not. So I came up with some results and presented paper in ISIT 2006, and then I did transaction on 2007 for power residue sequences and for Sidelnikov sequences. And we have an interesting development from then, especially on the line of Sidelnikov sequences. And this talk is all about such development so far, and it is still going on. So I'm not going to prove anything today. I'm just trying to explain what's been happening in this line, and also some of the things that I'm going to talk could not be the truth. It's just my understanding from the known results or published results. And I guess one of the participants is here, Professor Yang is here, so he may be able to correct what I'm, if I'm possibly incorrect. Well, so the first family that I presented was the idea of changing the primitive element. So it's just very natural way to consider or to construct many sequences of the same length, same alphabet, using the same technique, and to check the cross correlation. And I was so happy that the cross correlations is very good. So there are the Euler phi function phi of m members can be constructed with the cross correlation upper bounded by square root p plus 2. That's quite amazing. And also for Sidelnikov sequences. Oh, and I used for still further some decimations and to produce cyclically distinct members in the family, and I found also very good cross correlation properties here. The one big picture that I used at that time was this. We have a power residue sequence and its constant multiples. By the way, what I have observed was changing the primitive element equivalently gives the same sequences that can be obtained by multiplying a constant term by term to the original power residue sequences. So we don't have to worry about changing primitive element. We just multiplying term by term the same constant. So they're not exactly one-to-one correspondence, but basically all the different sequences can be obtained by changing the constant. So so the constant multiple idea comes, I guess, from this. And given a power residue sequence and using all different constants, we have this red line of sequences. And by taking the all possible decimations, we have these members of the sequences here. And I was able to show that the cross-correlation bound is bounded by square root p plus 2. And any of them here and any one of the other member has also a very good bound. However, in the same set, the cross-correlation is not as good as the previous cases, because can be as big as the period p. Anyway, and the same idea also applied to the Sidelnikov sequences. So instead of changing the primitive root, I just take a constant multiples. So I was able to construct set of M-ary sequence families, one from the Sidelnikov sequence. And the constant multiple is not necessarily a Sidelnikov sequence in general. So only the one member is a Sidelnikov, and the others are all different constant multiples of that. And I was able to show the cross-correlation bound is bounded by square root of q plus 3, which is marvelous. So even though the family size is quite small, because the original sequence has alphabet size m, so only the maximum number of members in the set or in the family is less than m. So if we are talking about, say, ternary sequence, we only have 2 or 3 or 2, because we cannot multiply 0 to get another sequence. So anyway, this was I guess a good start. And the major improvement from that, I think, I'm not sure, but came from the some observations and conjecture by Guahu and Kwan in IEEE electronic letters on constructing families of sequences using Legendre sequence, which is another character sequences. You know, it's very famous. It's quadratic characters. And they presented the result that taking a shift and add, that's a key idea, shift and add. As in the construction of gold sequences. Using a Legendre sequences, they were able to construct family with very nice correlation property, but unfortunately they were not able to prove it. And they showed some graphs of cross-correlation of a pair of sequences in the family they constructed. And the very next year, or was not very next year, it was 2002 and 2006, J. Rashanen proved the conjecture, and the correlation upper bound was shown to be 2 times square root p plus 5. So he used the sum of the quadratic characters inside the argument is a quartic polynomial, which is simply a product of 4 linear polynomials in order to prove this correlation bound. And I think from then on there are 3 major papers that improves the line of constructing M-ary sequence families using Sidelnikov sequences. I think they got an idea from this shift and add technique, and then well, the use of while bound on character sums is a very well known technique for a long time. So it's just a matter of picking up which one to prove the right theorem. So in 2008 and 2009 and 2010, in a series of papers, they presented the results that they claimed that they were able to construct families with a still larger size by adopting a shift and add technique of Sidelnikov sequence in addition to constant multiples. So they take constant multiples of Sidelnikov sequences, and then they take all different possible cyclic shifts, and then they choose pair, and then they add up, and then they produce a lot more members in the family. And major technique was the while bound on character sums to show the cross correlation bound. Anyway, the while bound, in order to explain what the while bound they used, this is very well known character sum bound of where the psi is a multiplicative character of finite field of size q, and d is the number of distinct roots of the polynomial f of x in its splitting field, and this is the original one that these two papers have used. The little tuning was to use the convention that psi of 0 is equal to 0, which is, conventionally or theoretically, it can be defined because psi is a multiplicative character defined only on the non-zero elements of the field. Anyway, successfully applied and proved a lot of things. In 2010, the Professor Kong in University of Waterloo modified the convention so that psi of 0 is equal to 1, and I'm not quite sure whether one can do this or not. But she was able to use this convention this time, and then a little bit generalized version of the earlier one on the bound. And this time we have summation of E sub I, where E sub I is the number of distinct roots in the field FQ of each polynomial, which were missing in the previous case. Anyway, so I will just briefly explain what these results are in the following few slides. I'm going to save alpha to be a primitive element of some extension field GFQD. I'm going to use beta or gamma for primitive element of GFQ, and psi is a multiplicative character with some appropriate convention for psi of 0. And this is the cross correlation that we are used to measure the correlation bound on the constructed or proposed family in the construction. So the first major improvement was given by these two papers in 2008 and 2009. This is the first appeared in 2009 and later, but almost simultaneously and independently, I guess, in 2008, with the set size just a bit bigger or a bit stronger in a correlation than those in 2009. So is this a typo? I guess not, because they appeared in only about 3 or 4 months difference, and the submission date are different and switched. So the one that appeared in 2009 has been submitted much earlier than the one that appeared in late 2008. So I think There's some interesting story going on there that I'm not aware of, possibly. But anyway, they adopted the shift and add sequence like this, given a Sidelnikov sequences of T, and its cyclic shift, and they use two different constant multiple or the same constant multiple, and then construct S prime of T, which is not a Sidelnikov, not anything, but members of a family that contributes very nice correlation bound. So this is one example of their paper. Given a Sidelnikov sequence, take all different possible constant multiples and shift and add of some type, and still different shift and add type for different shift. And correlation is bounded by 3 times Q plus 5, and the family size is now much bigger than the first family. So in order to explain the next step to improve this research, I have to get back to the Sidelnikov sequence definition one more time. Guangong has found quite interesting representation of Sidelnikov sequence that's been defined like this, which is the discrete logs of beta to the t plus 1 mod m. And I think just she neglected this part, the red part in her paper, because it's just one trivial case. But anyway, this should be this is necessary for this. Otherwise, if beta to the t plus 1 is 0, discrete log of 0 is not defined anyway. Well, usually this discrete log value belongs to the integers mod q minus 1. So in order to reduce that down to M-ary sequence, we just take mod m. So that's a very simple explanation. And as soon as I see this is nothing but a add one table of finite field. That's well, I think this is very interesting observation by myself. I'm not sure you are the same is true for you. Huh?
What is this table?
Add one table. I'm going to explain what add one table is. It's just well, probably different in math area, but in double E area, when I teach finite field 101, I always introduce add one table for computing the multiplication of, or the addition of field elements written multiplicatively using primitive element. Yeah, exactly. So, well, the name add one table comes from I guess from Dr. Lloyd Welch at USC. Yeah. He used add one table, the term add one table there. So this is the success powers by beta, and add one, and then take the log to get the power of primitive element of this. So that you can add two members of fields very easily by factoring the least power of beta of the two to leave one with the add one form like this. So this is exactly the sequence, Sidelnikov sequence that I showed earlier. I took the Q is equal to 13 for that purpose, and I have to adjust this case that beta to this t plus 1 is equal to 0. So anyway, Professor Gong has contributed a very interesting contribution to the structure of Sidelnikov sequence. She's famous for the inventing an array structure to construct the sequence families. She applied the array structure, and in order for that, she found a construction of Sidelnikov sequence, not directly, but using self-field elements. So when we consider not of period q minus 1, but of period q square minus 1, now we change the size of field from q to q square, we still can use the same definition using the primitive element of g of q square, but instead of that, we use primitive root beta of g of q, and then some trace representation of alpha of t, and we take the discrete log, we obtain the same Sidelnikov sequence of period q square minus 1. And then she write this sequence of period q square minus 1 as an array of size q minus 1 times q plus 1, and then observed and proved that the first column sequence is a constant multiple of Sidelnikov sequence of period q minus 1, because this is the number of rows, and the period of the column sequence is q minus 1. And all other column sequences have a very nice cross-correlation value, and also the constant multiple of all other column sequences too. So in addition to constant multiple and shift and add, she newly adopted the column sequence of this array to increase the family size, maintaining the cross-correlation bound. And this is an example of her choice in her paper, QB7 and the 6-ary Sidelnikov sequence of period q square minus 1. That's 48, and we write this as a 6 by 8 array. And then the first column is the constant multiple of size, of smaller size. And then these column sequences are not all cyclically distinct, but have some repetitions, like this column sequence is the same as this one is same as one shifted version of this, etc. So she found the representation of each column sequences as this, and then finally constructed sequence families in this form. This is only one of the examples in her paper. So she takes constant multiple and shift and add, and then a lot of constant multiples of column sequences in the array. And family size is greatly increased by factor of, I guess, m. Oh, maybe this is a typo. And the maximum correlation is still maintained by 3 times q plus 5. So I guess there is some magic in this expression of 3 times square root of q plus 5. So we still don't know whether the size of this family is the maximum possible. And by the way, this result is presented earlier in 2009 ISIT, and in that conference session room there is Professor Kim with me, and he picked up the idea and immediately generalized, so that why not considering of still longer length, like q cubed minus 1, q fourth minus 1, in general q to the power d minus 1, and then write down the array of size q minus 1 times whatever left appropriate, and then well, the to make it short, he was able to prove that all the column sequences in this new array, of much bigger array, have the same cross-correlation bound. The harder part was to identify the cyclically distinct column sequences of the array, because when in earlier version where only the number of columns is q plus 1, there is a very easy and immediate relation. But for when you go up to q to the power d minus 1 and then down to size q minus 1, we have to figure the q cyclotomic coset modulo q to the d minus 1 over q minus 1. That's quite irregular pattern. So I'm sorry, it's blocked here. So still the correlation is 2 times d minus 1 times q plus 1, and the size, family size of these column sequences itself, without considering, even without considering the constant multiple and shift and add, was about this, n minus 1 times q to the d minus 1 over d, and this is the one bigger example than the previous one, where we go up to q to the cube minus 1 and then write this as a 6 by 57 array, and then the first column is a constant multiple of Sidelnikov sequence. By the way, constant multiple now becomes only a binary sequence. So I'm wondering if we can say this as a 6-ary sequence. Well, it's not exactly false, but might have some problem. Anyway, so we have to distinguish identify cyclically distinct column sequences in this big array. So he was able to identify which one is which, try to figure out a lot of relations among the column sequences, and then this is the size of the family for d is equal to 2 and d is equal to 3 and d is equal to 4, and I was surprised to see a lot of big numbers here. Even factor m minus 1 is omitted. So you can increase d as you wish to be as big as possible, and then you can construct as many sequence family as possible, still maintain the length, the alphabet size of the sequence, and the cross correlation bound. So that might imply something very interesting further that I need to think about, and I ask you, all of you, to think about from now on. This is very surprising, because I'll repeat one more time. We fixed the length, we fixed the alphabet size, and we fixed the correlation bound, and you can increase the member of the family as large as you wish by increasing the power d. There should be something I'm missing, or he's missing. Anyway, so this is the summary of the results so far. I presented size n minus 1, very little. But immediately Professor Yang and Professor No, they improved by taking a shift and add, and then Huang added a lot more by, oh my gosh, this is not as bigger than this. It's smaller than this. What's happening here? Probably this is, there is a little typo here. So she enlarged the family size by adopting the array structure of the longer Sidelnikov sequences, and including a lot of different columns. And then Professor Kim generalized this so that now we consider still longer Sidelnikov sequences and get down to size q minus 1. And the correlation maintains or remains comparably in this case. But here, observe, this is Q2. When D is 2, this is just Q. And when D increases, we add up the factor of Q here. So that's quite a huge increase, I think. I'm almost done. So this year, I'm trying to improve this a bit by employing decimations, but the result is not complete yet. We found some some possibility of succeeding improvement, but I was not able to prove yet, so I just stop here. Thank you very much.